In this lecture, I'm going to talk about critical design sections for shear and torsion. So the first question is, what is a critical section in a structural member? So a critical section is the section at which the load effect is maximum. So to illustrate, let's talk about something that we have discussed before, which is critical sections for bending or flexure. So say we have a structure that looks like this, and we have a uniform load acting on this member here, right? When we draw the structural model for this member, right, we're going to go with the center line right here, center line right here, and we're going to end up with something that looks like this. When we draw the moment diagram, we're going to end up with a moment like this, then a constant moment down on the column. So to which moment should we design for? Should we design for this moment right here, which corresponds to this point right here? The answer is no, right? Because the critical section for this beam is right here at the face of the column. So that's the critical section. Why? Because when this beam cracks due to this load, the crack will occur right there, right at that face. It won't occur in here. It will occur right at the face. And so when we look at the bending moment, if the face of the column is right here, this is the critical section, and we're going to design for this moment. This is important because this moment here is going to be our MU, and it's going to be a little less than this value here at the joint. And so that will allow us to design a slightly more economical section. So how does this translate to shear? And you can find this in ACI 11.1.3. When it comes to beams subjected to loads that are acting on the top face of the member, the critical section for shear is located at a distance D away from the support, right? Where D is the distance from the rebar in tension to the maximum ending compression. So that's our D, right? So the critical section is a distance D away from the supports. And the reason this happens, if you look at this drawing here below that shows the cracked beam at failure, you see that once the beam cracks, this portion of the beam right here is the one that will fail, and only the load on that portion of the member is actually pushing the beam down. So at this point is where we have to check the shear. That's the shear that will actually make the beam fail, and that's the critical section for shear, so long as the load is applied on the top of the member. And the reason the distance is D is because the shear cracks occur at 45 degrees, and so we have D vertical, D horizontal, same distance. Now there is an exception, and that is if there is a load, a point load, that is within that distance d, then the critical section has to be moved to the face of the support. And that makes perfect sense, because in that case, that load P is now creating also part of the failure surface. And now the critical section has to be moved back in order to account for the presence of that load. Another exception occurs when the beam is loaded at the bottom, right? So if you have a load acting at the bottom of the beam, such as in the case of a beam that has a ledge and carries a load near the bottom of the member, when we draw the failed structural member right here and we draw the cracks, we see that the free body diagram of that member after it fails includes all of the load along the member. And so you can't reduce the shear at the critical section, and so in this case the critical section is at the face of the support if the load is acting near the bottom of the member. Another exception is when a member is supported by columns that are hanging. So like in this case, the two columns supporting this beam are right here, and basically the beam is hanging from these columns. So in this case, again, when you draw the failed member, you draw the cracks and you look at the free body diagram, most of the load is in that free body diagram, in that part of the member that failed. And so you can't reduce the maximum shear. So the critical section is again at the face of the support. If you have a continuous beam or a frame, this is another case where you are allowed to select the critical section for shear at a distance d away from the support. This is the typical case in most building structures. So if you look at this example here, let's just try to solve this to have a sense of how much of a reduction are we getting from taking the critical section at a distance d away from the support. So say you have a live load of 8 kip per foot, a dead load of 5 kip per foot. You compute the ultimate load combination, which is 1.2 times 5 plus 1.6 times 8, and you get 18.8 kips per foot. The reaction is this value here, UL over 2, but we have to subtract the shear that is inside of the distance d away from the support. So that's U times d. So in that case, we have U, which is 18.8, times L over 2, which is 25 divided by 2, minus d. And let's say this is a beam with the following cross section, as shown right here, top right. Depth of 24 and a d of say 21 inches. So that would be 21 divided by 12 to take it to feet. And so this results (18.8) times 10.75 202.1 kips. You can compare that with this value here, which would be 18.8 times 25 divided by 2. Which is 235 kips. So there is, a significant reduction, which is not trivial, about, let's see, it's about 14% reduction. So that's significant. So we're able to design for a smaller shear force because the critical section is at a distance d away from the support, just like it's shown in this case right here. A couple of cases here for you to think about. So let's say we have a beam that has a depth of 30 inches, so D is 30 inches. Say it's in cantilever, the load is applied on the top of the member, and it has a point load located 5 feet away from the support. In that case, where would the critical section be? I'll let you think about it for a little bit, but in that case, remember that the exception is when the load P is inside the distance D. And in this case, the load is outside of the distance D because it's 5 feet, which is greater than 30 inches. So in that case, the critical section is going to be at a distance D away from the support. In this case here, to draw the support, we have a simply supported beam with a point load 1 foot away from the left support, and that is less than D. So the critical section is going to be right at the support in that case, although in the other side it is at a distance D. In the top right here we have a cantilever with a load located at 2 feet away from the support that is less than 30 inches. So in that case, the critical section is right at the support. Bottom right here, D, we have a beam with a hanging support on the left and a vertical support on the right. And so for this case here, the critical section here is at a distance D, while in this case it's right at the support. Same thing happens for torsion. If you have a member and it's subjected to torsion, you are allowed to take the critical section for torsion at a distance D away from the support, unless again you have a situation where you have a point torque applied within that distance D, and then in that case the critical section has to move back to the edge of the support.